Hi everybody, this is a relook at arc segments and sectors, this time with degrees, and later we'll do it with radians. Now when I recorded this the first time I made a transposition error here. Oh no, it was here. I wrote 60 instead of 06, so I'm re-recording this for you so you can have the correct answer this time. So we start with two circles and we put a belt around it. We want to find out how long is this belt. And the question actually asks us what's the radius of a circular belt. So we're going to work that out in the last step. So we start with this diagram, and I've added in these two rectangles here. Now given that these lines are tangents to the curve, that must be a right angle and that must be a right angle. And that creates this rectangle here and this triangle here. Now if this side here is 3 because it's a radius, this side must be 3. If this whole radius is 15, this remaining part here must be 12. This length here from the question is 20. So if we have this length here 12 and this length here 20, we can find out these two angles here using our trigonometric ratios. So our first step will be to find this line here from B to C. I've labeled this point here B, and by using Pythagoras' theorem with this triangle, which I've redrawn here, we can find out that BC is 16. Now because BC is parallel to DE, that gives us this length here, which is part of the length of the belt that goes around both of them. Our next step is to find this angle here, because if we find this angle, it's the same as that angle. These two angles are 90, the whole angle is 360 degrees. So we can subtract these angles here from 360 degrees to find gamma. So sine theta equals 12 on 20, opposite over hypotenuse. There's the opposite side, there's the hypotenuse. Which gives us an angle of 106.26 degrees. Let's put the degree symbol on there. Now a minor arc, as I said earlier, it gives us 36.87 degrees. That's this, times that by 2, that gives us this part. Add 180, that gives us this whole angle. Subtract it from 360, we get 106.26. Now we can find the minor arc, so from here to here. That will be gamma divided by 360 times the circumference. So that will give us 5.5637 centimeters. We've found this part. We've found these two. All we've got left is to find that part. To do that, we know that alpha is equal to 90, take theta. This triangle is 180 degrees, that's 90 degrees, we know this one, we can find out that one. That gives us, we'll have to correct that now. Or do we? No we don't, because that angle was correct. Now, so 53.13, 2 times that gives us 106.26, which looks remarkably like this. We know that this is 360 take 2 pi, which is 253.74. We can now work out the major arc, which gives us 66.43. We can now eliminate the error that I made earlier. This here is 5.5637. So I'll write this bit here neatly. Now we add these up. I'll grab my calculator here. 2 times 16 plus 5.56 plus 66.43 gives us that number. We can find it as a decimal. which gives us 104. As per found by somebody's dad. Hello, Dad, if you are watching. And that's quite a good problem. You could probably do these last steps a little bit easier because I'm guessing that there's some geometric property here. Let's quickly go through what happens with arcs, sectors, and segments again. An arc is a proportion of the circumference. To find the length of the arc, multiply it by the proportion required. So if the whole circle is 360 degrees, we can create a proportion by taking the angle and dividing it by 360. That's this part, and then multiplying it by the whole circumference. So 86 degrees of a circle of radius 5 would be 86 divided by 360 times by 2 pi 5, which in this case would be 7.5 centimeters to 2 decimal places. The arc of half the circle, we just multiply by a half, and that gives us this answer here. The perimeter of half a circle with diameter 90. Now the perimeter means the length's all the way outside of the shape. So we would find the arc and then we would add the diameter. It's different to just finding the arc. So you can see here I found out the arc and then I've added on the diameter. If they give you the radius, just remember to use the radius correctly, you may need to double it to find the diameter. Now a sector is just a proportion of the area of a circle. So to find the area of a whole circle, we would use pi r squared. To find the proportion of a circle, we'll take a proportion and then multiply it by the whole circle. So again, if we have 86 degrees and the length is 5 centimeters, we would have 86 on 360, which is the proportion of the circle, multiplied by the area of the circle, which will give us 187.6. And we call this a sector. If we took half a circle, same drill, but we have to remember, don't use the diameter, use the radius. Thus we're using 45, not 90. Half times pi r squared equals 3,181 millimeters squared. Remember your units if it's an area. We're using it as a squared unit. The third part of the exercise draws a chord from one part of a circle to another. Now, where you do this, you can connect two radii to it, and it'll create some segments. We call the smaller segment the minor segment, we call the bigger part the major segment. And that's where a chord sections a circle, makes different regions. And there's a way of doing that too, so I shall show that in a second. In example 1, we are simply finding the minor arc AB, so that's this length around the outside of the circle. 40 divided by 360 times 2 pi the radius, that gives us 34.9. If we want to find the area, if we want to find the length of AB, we can use the cosine rule. Z squared equals A squared plus B squared, take 2BC cos A. 50, that's this length. 50, that's this length. 40, that's the angle. 2 times the sides on either side of the angle. That gives us this squared value. Take the square root, you get 34.2, and that's this length here. Example 2, this time they want us to find the area of the minor segment. So the area of the minor segment is this area in here. To do that, we're going to find, what are we going to find? We're going to find the minor sector, which would be this part, and then we're going to subtract this triangle here. So, using our sector formula, though I've done it in 2 steps for some strange reason, over here is the area of the whole sector. Over here is the area of the triangle. If I subtract them, which is what I've done here, you get this area over here. Example 3, what are we doing here? Again, we're finding the area of the minor segment, but this time we're doing it with exact values. So we know the area of this circle is 16 pi. We know the area of the triangle AOB would be a quarter 4 times 4 sine 120, which gives us 8 sine 120. Now we can't use a calculator because we're looking for an exact value. It's typically a non-calculated question, so we need to find out what sine 120 is. Now from last exercise you'll know that sine 120 is equivalent to sine 60 in the first quadrant, which is also root 3 on 2 using your triangle. Maybe I could draw that. So here's our cast diagram. We know that this angle here is the same as that angle there, and sine is positive in the second quadrant, which 120 degrees is in the second quadrant. That should be a C, not an O. So there's 120 degrees, that's 60 degrees. Go back to the first quadrant, find 60 degrees, stop moving around. Here we go. So we need to find sine of 60 degrees, 60, root 3, 2, 1. Sine of 60 degrees, root 3 on 2. Thus, that's where that comes from. So to find the area of triangle AOB, it's 8 times root 3 on 2. 8 divided by 2 is 4. That's how we get 4 root 3. Now the area of the minor sector AOB, that's a proportion of the whole circle. So 120 divided by 360 times 16 pi. We worked out 16 pi up the top here. 120 on 360 is a third. A third of 16 pi is 16 pi on 3. Therefore, the area of the minor segment would be the whole sector minus the triangle. The whole sector is 16 pi on 3. The minor segment is minus 4 pi, minus 4 root 3. Don't forget your units. Don't forget the squared. And that is the corrected first exercise of chapter 2. Thank you, everyone.